I'm going to look at question 2 now, the analysis question, the temperature one here. I'll assume you've read it, so I'll just focus in on the key points. So number 1, we've got an equation here. You'll always be given an equation. And it'll always tell you also what's going to be plotted on which axis. So that's key, and you can see that I've circled that down below. So we can see that this will be plotted on the y-axis and t on the x-axis. Make sure you can see that, because the thing that's plotted on the y-axis, you need to rearrange this equation so that that is the subject of the equation. So ln natural log of theta minus theta r, we need that by itself. So the first thing I'm going to do is make theta minus theta r by subtracting theta r over to the other side. That gives us this first line here. And then what we need to do is, you can see a clue from here, we're going to be taking the natural logs. Why? Well, that's going to remove the exponential function. So a good trick is if you ever see an exponential function in the equation, you're going to be doing a natural log linear graph. Now you will need to take a log, and that will remove the exponential function. So once you've done that, just taking the natural log of both sides, you see we get this here. Now this goes on your y-axis as stated up here. On the x-axis is t, as I've highlighted over this side. So that leaves 1 over k with a negative as the gradient. So negative 1 over k is the gradient. And the other part in front of it will just be the y-intercept. So natural log of theta 0 minus theta r. It will always be the same question 1, so make sure you're comfortable with that. Scrolling down now, you have to complete your table. I've done it, but I'm just going to point out a few points here. To get this, you're just doing a simple subtraction using the constant below. How do we get the uncertainty? Well, if you look below, you can see that over here, the uncertainty is plus or minus 0.5. Here it's plus or minus 0.5. So we are subtracting, and then when you subtract two values, you add together the absolute uncertainties, and therefore we get plus or minus 1. Now, talking about sig figs, how do I know that this numbers are to 3 significant figures? Well, the calculation is based off this number, which is 3 sig figs, and this number down here, which is 3 sig figs. So I'm giving my answer to 3 sig figs. Remember, if it's a calculated value, you match sig figs. Okay, that's really important. For uncertainties, you match decimal places, dp. So this was to 1 dp, so my uncertainty is to 1 dp. Now, taking the natural log of those values. So what you do is obviously take natural log of 56.5. Now, why I've done that many sig figs? Well, important to highlight this point, which I've actually put here so you can read it. For logarithmic quantities, the number before the decimal point is not counted. So that's really important. So you can see that this calculation here is based on these two, which is this, and that is to 3 sig figs. Now this is a calculated value, so you might be thinking, hey, I need to do this to 3 sig figs, but remember we don't count the number before the decimal for the logs, so that doesn't count. So that's why we end up with these here, which are the 3 sig figs. So you end up looking like you're going up one more, but that's because of that rule above. Don't forget that. So natural log or log base 10, remember that the number before the decimal doesn't count, and then you still follow the rule that you're matching sig figs because it's a calculation. Now, how do you calculate the uncertainty? Well, to calculate the uncertainty, what you have to do is, there's no other way of doing it, is unfortunately just trying the smallest or largest number and subtracting from that. So we're going to do the natural log of 57.5 minus the natural log of the actual value, 56.5. So it's kind of a brute force. And you have to do it for each one separately. So this one here would be the natural log of 47 minus the natural log of 46. One of that difference is will give you the uncertainty. Remember, for the uncertainty, we're matching dp. So you always calculate after you've done this one, and this has 3 dp, so this one needs 3 dp. Once you've done that, it asks you to calculate, draw the graph. Now, I've drawn it here electronically. You'll be using a sharp pencil. These lines are too thick. And you'll be doing it neatly. My error bars aren't done with rulers. But your graph should look like this, so do check that. Now, for the line of best fit, they've strictly said that it's got to go through this area here. So somewhere in this area. So at 3.7, it's got to go between, what was that, 16 and 17. So it should go between 16 and 17 at 3.7. And down here at 3.2, should go between 31.5, which is that one, and that will be 31, 32, 33. So it's got to go between 31.5 and 33 to get it. You can see it doesn't go quite through all the points, but say I've got a sim number above and below, so that line of best fit's valid. I've labelled it, really important. Now the line of worst fit should always cross the line of best fit, and I always kind of start at the top up here and kind of adjust it as I need to. So you've drawn that line, you kind of adjust until you're going through all of the error bars. It's got to go through all the error bars, that's really important. And it's got to, so you can see here, it just goes through the error bar here, through this one, you check just in there and just in there, so it's perfect. I've gone for the steepest possible. That's my line of worst fit. Now for your gradient, key thing that people forget is they do cute little triangles like this big, because the numbers are easy. No, you've got to use at least half a line. So I've actually gone from here all the way to the bottom. The bottom's nice and easy always, because you can read that off here. If I was doing this in the exam as well, I would be kind to my examiner and show the triangle that I'm using, so they can quickly check my values. Another nice thing I've seen done is people actually kind of label the points so that the examiner knows you've read them off correctly. So this would be 3, so we actually do x-axis first, 35, 36, 37, 38.5, comma 3.0. So you can do that if you want to. Just make sure you're going off your line of worst fit for both. The common mistake is people use this point here, and then for the green line, and then use the red line. So you're doing two different lines, but you've got to do it for both lines. You've got to do the gradient for both. It's a bit tedious, but that will give you 2 for your line of best fit. Changing y over changing x gives me this value. And then for my worst fit, again, same thing, gives me this value. Don't forget the negative because the line's sloping down. And then that gives us a gradient of this. That was for my line of best fit. And then if I subtract this from this, you see that we get an uncertainty of 0.0012. People often ask, do I need to now do, I did the steepest possible line. Do I need to do the shallowest possible line? You can do, but you don't have to. One's sufficient. Now to determine the y-intercept, what you'll need to do here is use the equation y equals mx plus c for your best fit and worst fit. Now obviously your gradients will be different and your y and x value will be different, but effectively that's what you're doing the same calculation. You're trying to find the y-intercept for both your best and worst fit and lay it out neatly so the examiner knows what you're doing. I'll now skip ahead and do the working. And there's my working. So I've used the y and x value from the bottom over there. Like I said, sometimes that's a nice easy one because obviously you know the free value is nice and easy, and then you can get those values from over there. I use my gradients, so you can see the gradient value here and here for your line of best fit, line of worst fit, that just came from above, times by the different y values. That gave us those 2 y-intercepts. One minus the other gives us the absolute uncertainty of 0.02, and the value is 4.22. And I always do a quick check. Is that sensible? Well, yes, if you look at that, this is 5 over here. So to get to 0 would be about over here, by which time that will shot up a bit further towards a value of about 4.2, which is what I got. On to the next question now. What I've done for you here is I've actually screenshotted question A and the information about theta r to find these values. So we know that the gradient equals negative 1 over k, and therefore I'd write that rearranged so the examiner knows you know what you're doing. So you know that k is therefore equal to negative 1 over gradient. It does want units, so we'll talk about these in a second. And then theta naught, well, how are we going to get that? Well, what we realise is that the y-intercept, I'm going to write that out in full actually, y-intercept equals ln theta minus theta r. So if we take the exponential function of both sides, e to the c will equal theta naught minus theta r, and therefore e to the c plus theta r will equal theta naught. So there's quite a lot involved here to find those values. Okay, I've skipped ahead and done the calculation. So for the k value, it's 1 over the gradient. Obviously, the gradient's negative, so the two negatives cancel. That gives us 31.6. As we said, this is the rearranged equation. So now I just put my values, e to the y-intercept, which is 4.22. We can see that up there. Plus the theta r value, which, say, was just told to us, and I've screenshotted, oops, over here. You can see 18.5. And then put that into my calculator and I get 86.5. Now these answers should be to 3 or 4 SF, given it's based on the values we've used. We don't really lose too much information. Now in terms of units, a lot of people forget to include the units. We know theta is a temperature, so it's degrees Celsius. K is a bit more tricky, it's 1 over gradient. And it's a constant, so we can't know just off the top of our head. Because remember, if it's something like EMF, we know it's voltage. If it's resistance, we know it's ohms. If it's temperature, we know it's degrees Celsius. But K is just a constant, so we don't know what the units are. But we know that it's going to be 1 over whatever the units of gradient are. And what are the units of gradient? Well, you go to your graph. Your gradient is just your change in y, this axis, divided by the change in x. So the units of the gradient... well, you write the equation for gradient, it's change in y over change in x. We just need the units in the change in y. Now, a lot of people go, well, the units are degrees C, but look at the brackets. That's inside the brackets. Then you take the natural log, and remember, if you ever take the natural log of anything, the resultant number doesn't have any units. So that's a key takeaway. If you log any unit, could be ohms or whatever number you get will have no units. Same if you do natural log. There are no units. So it's no units over the units of the x-axis minutes. So it's no units over minutes. So the units are minutes to the -1. Because no units is just like 1. So minutes to the -1 are the units of the gradient. So if I put that into there, we've got 1 over minutes to the -1, which just becomes minutes. So unit is minutes. Don't write M, because that's meters. Min or minutes is good. I'll just write out the whole thing. Next one, determine the absolute uncertainty in theta naught. So I brought down the equation we used to find theta naught. Now, because we've got the exponential function here, that confuses things. Remember, if you've got the exponential function log or natural log, when we're doing uncertainties, you just got to do the kind of really frustrating kind of brute force method where you've got to put in your largest or smallest and just work it out. So we know the actual value is 86.5. Let's now try the largest possible value. So we'll do E of your largest value of C. Now C was the y-intercept. The largest value is 4.24. So do maximum possible value here. Plus our maximum possible value of theta r, well, we can get that from here, is going to be 19.0 to give us a theta naught value. Put that into my calculator. We get 88. Theta naught of 88.4. Now you can see the value that we got there is 86.5. So the absolute uncertainty will be 88.4 minus 86.5. Now remember, there are other ways to do this, and I'll talk about it in a second. You could also do the minimum, maximum, but that gives you an absolute uncertainty of 1. And now we need to match dp here, so 1.9 as our absolute uncertainty. Okay, and that's for theta naught. Now again, what I said is you could use the smallest possible value, so you could also do e to the 4.20 plus 18. Or you could do your largest minus your smallest and divide by 2. So range divided by 2, but that's extra steps. So I would just do your largest or your smallest. And just remember this key takeaway: whenever it's a log, natural log, or e, to find uncertainties, there's no tricks. You've just got to try your largest value and subtract it from your actual value. And that will give it to you. Okay, so it's a bit of a tedious brute force. A final question. I suppose one way, or potentially the kind of the way that requires the least new knowledge or playing around, is actually just, let's just rearrange this equation. I know we've already kind of done that above, but let's just do it again. So you end up with ln theta minus theta r. Remember, that's because we subtract the theta r across and then natural log it. And then we end up with ln theta naught minus theta r minus t over k. So we want to find t. Let's rearrange for t. So t is going to be ln theta minus theta r minus ln theta naught minus theta r. So a bit tedious this way, but as I say, this is probably the one that involves the least kind of new thinking. Now that we need to get k by itself, so we're going to times by -1 and also times by k. So we actually end up with minus k at the front once we've done all that. And that's t. Now we've got a value for k, it's up there. So now we just put all our numbers in, being careful to get them all correct. I mean, I could tie this up mathematically, but I'm not going to. We know it's 25.0, and we know theta r is 18.5. Now remember, there's no uncertainties here, so we're just doing the actual values. Theta naught, no, what was theta? Oh, there, 86.5, I got it up there. So 86.5, so using all the values you've got now, and of course you get error carried forward if need be. And you're basically solving that and getting an answer. It's in minutes, so there's no need for units. I'll type it in now and write my answer. I get 74, which, hey look, let's have a check actually. Let's see how sensible that is. But now all these numbers are to 3 sig figs, so I can give my answer to 3 sig figs would be ideal there. Let's see if that seems sensible. Drop to 25. Oh yeah, no, we can't really do a sensibility check on here because we don't have enough points. It's beyond the end of that graph. I guess we could work out what ln theta minus theta r is and check if that's sensible. So that's what's on the axes. So ln theta, which is 25, minus theta r, which is 18.5. That gives us 25 minus 18.5. Gives me 1.87. So I'm going to my graph and going, where's 1.87? Oh yeah, it's way down here, so the time's going to be way over there. Yes, so 70 seems sensible because it's off the graph there. Hope that made sense. If there's any questions, let me know.